Hi everyone, let's look at this question on geometric series. Find the set of values of x for which the geometric series sum from 0 to infinity of x minus 1 all over x plus 2 raised to the power r, where x must never be equal to negative 2 converges. Okay, so we want to get a set of values of x for which this series will converge. Alright, for a series like this to converge, it means there is a finite sum. Okay, now we know that for convergence, this absolute of the common ratio must be less than 1. So what we need to do is to find the common ratio and find the solution set of this inequality. Okay, let's take the series. Okay, this is a series. The general term of this series, Tn or Tr, is x minus 1 all over x plus 2 all raised to the power r, so that we can see that our T1 will be, let's just follow the same line. Our T1 will be when R is, look at it, T1 here simply means first term. The first term, we look at where R starts. R starts from 0. So our first term is when R is 0. We should not make that error to say T1 means R equals 1. R starts from 0. So our first term is when R is 0. So we're going to have x minus 1 all over x plus 2 raised to the power 0. And anything raised to the power 0 is 1. The second term, see, R progresses from 0 to 1 to 2 to 3 and so on. So our second term, when R is equal to 1 and not 2, R should not be equal to 2. So we have x minus 1, x plus 2 to the power 1. Any expression raised to the power 1 gives us the same expression. From here, we have the first two terms, and we're told that it's a geometric series. If it's a geometric series, we can get the expression for R. The expression for R will simply be T2 all over T1. Our T2 is x minus 1 all over x plus 2, all of that divided by T1. Anything divided by 1 will just give us the same expression. So this is our common ratio. This is the expression for the common ratio in this series. Now, having the common ratio, all we have to do now is to solve for the solution set in this inequality. We have to solve for the solution set in that inequality. It's the same as saying, all right, this is the same as saying absolute x minus 1, x plus 2, less than 1. And this expression is the same as saying that negative 1 less than x minus 1 all over x plus 2 less than 1. Or so we have this situation, or the root of x minus 1 all over x plus 2, okay, all of this squared less than 1. So we either solve this or we solve that. So we're going to handle the two cases and see if we get the same result. Let's start with this one. Let's start with this one, method 1. Method 1. Okay, this is the same as this. Let's work with this. So we have this square root. If we square both sides, this square will cancel that square root. We're left with x minus 1 all over x plus 2, all of this squared less than 1. 1 squared is 1. We have this inequality to solve. Alright, so we're going to square this numerator and square this denominator. Squaring that numerator, we have x minus 1, x minus 1, x plus 2, x plus 2 less than 1. So let's open the parentheses. We have x multiplied to x is x squared, x multiplied to negative 1, negative x. Negative 1 multiplied to x, negative x. Negative 1 multiplied to negative 1, positive 1. X multiplied to x, x squared. X multiplied to 2, 2x. 2 multiplied to x, 2x. 2 multiplied to 2, 4, less than 1. So this gives us x squared, negative x minus x, negative 2x, plus 1, all over x squared, 2x plus 2x, 4x, plus 4, less than 1. Okay? Now, this is a rational inequality. And to solve rational inequalities, we are always advised to make one side to have 0. Okay, let's bring this positive 1 to the left-hand side so that we'll have 0 here. So we're going to have x squared minus 2x plus 1 all over x. This one down here, we can, all right, let's put it there. X squared plus 4x plus 4 minus 1 less than 0. We have taken this positive 1 to the left-hand side, so I'll have 0 on the right-hand side. Now, let's put everything under the same denominator. Remember, this is the same as negative 1 all over 1. Let's bring everything to the same denominator. That means the LCM of this expression and 1 is just their product. This expression multiplied to 1 is that same expression. This expression divided by itself is 1. 1 multiplied to that numerator, we have just that numerator. This expression divided by 1 is itself. 1 multiplied to negative, this expression multiplied to negative 1 will be negative 1 into the expression. Now open the parentheses, we have x squared minus 2x plus 1, negative 1 multiplied to x squared, negative x squared, negative 4x, negative 4, all over x squared plus 4x plus 4 less than 0. X squared minus x squared 0, negative 2 minus 4, negative 6x, 1 minus 4, negative 3, all over. This down here, we can just write it again as x plus 2 all squared, less than 0. Okay, this, it came from the squaring of x plus 2. When we squared this, we got it like that, and we got it like that, and we got it like that. All right, so we just moved again from this form back to that original form. It is x plus 2 squared. Okay, now we arrive at this rational inequality. Negative 6x minus 3 all over x plus 2 all squared less than 0. We have to solve this rational inequality. If we look up there, we see that negative 3 is common, so we can factorize out negative 3, and so we have 2x plus 1 here, all over x plus 2, all of this squared less than 0. This is the inequality that we have to solve. So we have to carry out our analysis. If we look at it very well, we'll see that the denominator here, this expression squared, no matter the value of x, we are always going to have a positive answer. Any expression squared will always produce a positive answer. So this denominator has no major role to play concerning our sign, the sign of our inequality. This denominator has no major role. This sign will depend on the numerator. Again, at the numerator, negative 3 is a constant. It will always be negative forever. Right? So it will also have no role to play in the overall sign of this rational inequality. So the only member that has a role to play concerning the sign of this rational inequality will be this 2x plus 1. This one is a constant, will always remain negative 3. This one will always be positive. So for us to have a negative result, therefore, since we already have negative here, all of our positive, so this guy here must be positive. this expression here must be positive for us to always have a negative result. Remember, less than 0 means negative. All right? So for that to happen, we must always have 2x plus 1 to be negative. Okay? So we'll say this will mean that 2x plus 1 must be negative. Sorry, must be positive. What am I saying? Positive. Because this one is already negative, which will bring in the less than 0, the negative. So we can't have negative multiplied to negative to give us negative. So this one has to be positive, since this one is already negative and this one is positive. So this one has to be positive, greater than 0. So that will simply mean that 2x is greater than negative 1, which therefore means that x should be greater than negative half. All right? So this is our solution set. That's our solution set. This will give us all the set of values of x for which this series must converge. Now, method 2. Method 2, if someone did not prefer this and wants to use the fact that absolute x minus 1 all over x plus 2 less than 1 is the same as saying that negative 1 less than x minus 1 all over x plus 2 less than 1. All right? So we now have this inequality to solve. We have this inequality to solve. Now, how do we solve this? The middle member will go with this left-hand member, and this same middle member will go with that right-hand member. So we're going to split it into two different inequalities. That's the middle member. It goes with this left-hand member to form the first inequality and will intersect our solution when we take that same middle member and the right-hand member. So this is the inequality. This inequality has been split into two. We'll get this solution and we'll intersect it with this solution to get our solution, the set of values of x. Okay. So we'll take this part. Let us take this part. Negative 1 less than x minus 1 all over x plus 2. All right? And then we'll intersect with that other solution. We're going to take this other one later. Let's start with this one. So we have this rational inequality. Once more, we should have 0 on one side of a rational inequality. So simply take this negative 1 this way to have 0 here. So we're going to have 0 less than x minus 1 all over x plus 2 plus 1. This negative 1 going this way become plus 1. Now let's solve this. This is fraction. We can make this one a fraction and we'll bring them all to the same denominator. The denominator will be the LCM of this expression and 1. This expression multiplied to 1 just gives us that expression. X plus 2 divided by itself is 1. 1 times that expression will have that same expression. X plus 2 divided by 1 is x plus 2 times 1 is x plus 2. So we have 0 less than 1. X plus x is 2x. Negative 1 plus 2 is positive 1 all over x plus 2. All right, our rational inequality has been reduced to this simpler form. At this level, we'll now look for what we call critical points. Our critical points are gotten when we set the numerator to 0 and solve. That means x is equal to negative half, and we also set the denominator to 0 and solve. That means x equals negative 2. So we have two critical points, negative half and negative 2. We place them on the right positions on the number line. Negative 2 is to the left, negative half is to the right. We have 1, 2, 3 zones to test. We take a value from this zone, for example, a value from this zone, any value to the left of negative 2, for example, negative 3. Negative 3 is this way. All right, so we'll put it there to see if we get a positive result. Remember, 0 less than this means this is greater than 0. Okay, it's the same thing as saying that 2x plus 1 all over x plus 2 is greater than 0. And greater than 0 means positive. Alright? So 0 less than that means this is greater than 0, hence positive. So our result will lie where we have positive results. Let's start. Take a value here, negative 3. We'll come and put it there. We're working only with our signs. 2 times negative 3 is negative 6 plus 1 negative 5. So at the numerator we'll have negative divided by negative 3 plus 2 is negative 1. Negative. Negative divided by negative, positive. So here we have positive results. Now let's take a value in this other zone. A good value here could be negative 1. Let's put negative 1 there and do the same analysis. 2 times negative 1 is negative 2 plus 1 is negative. We're interested only in the sign. Negative 1 here plus 2 will become 2 minus 1, which is positive. Negative divided by positive is negative. We'll take a value this way. A good example could be 0. 0 is to the right of negative half. We'll carry out the same analysis. 2 multiplied to 0 is 0, so we'll have positive here. 0 here, we'll have positive 2. Positive divided by positive, positive. Alright, like we said, we say our solutions will lie where we have positives. So our solution will be either x is less than negative 2 or x is greater than negative half. So solution set here will be x less than negative 2 or x greater than negative half. This is our solution set for this part. Now let's do the analysis on this other part. Let's do the analysis on this other part. See that method 2 is really long, then it is worth knowing. Let's take this other part. It says x minus 1 all over x plus 2 less than 1. Here we already have everything in its reduced form. This rational inequality is already in its reduced form. Alright, so but we're supposed to have 0. Pay attention. It's not already in its reduced form, but we're supposed to have 0 on the right hand side. So we take this one this way. We have x minus 1 all over x plus 2. This is positive 1. Taking it this way become minus 1 less than 0. Alright, this is a fraction. This one we can also make it a fraction so that we bring everything to a common denominator. The common denominator will be the LCM of this expression and 1. And the best LCM is just their product, which is x plus 2. X plus 2 divided by itself is 1. 1 multiplied by that numerator is the same numerator. X plus 2 divided by 1 is x plus 2 multiplied to negative 1. So we have negative 1 into x plus 2. We must be careful with our signs. Now let's open the parenthesis. We have x minus 1, negative 1 multiplied to x, negative x. Negative 1 multiplied to 2, negative 2. All over x plus 2 less than 0. Okay, so we have x minus x 0, negative 1 minus 2, negative 3, all over x plus 2 less than 0. So our inequality reduces to this form. Our inequality has reduced to this form. Now, less than 0 means negative. Now, if you look at the numerator, we already have negative 3, which is a constant. It will never change. So, the numerator is already negative. So, for this rational expression to be negative, the denominator must be positive. Okay? So, all we have to solve for is the inequality x plus 2 greater than 0. This denominator has to be positive. Okay? So, from here, we'll see that x is greater than negative 2. Alright, so what then is our solution for method 2? Our solution for method 2 is the intersection of this solution and this solution. Let's do the intersection up here. So our solution will be the intersection of this solution and this solution. Let's take this first solution and we'll show it on the number line. We have negative 2, negative half. Alright, we have x less than negative half. Open circle and it goes that way. And we have x greater than negative half. This one is negative 2, sorry. So we have our arrow going that way. This is the representation of this solution. Now let's represent this other solution. This is negative 2. It says x must be greater than negative 2. That means all values this way. X must be greater than negative 2. Now, what then is the intersection zone with these two number lines? Remember, intersection zone means zones where we have solution in both number lines. Part of the solution is this way. There is no solution here. Part of the solution is this way. And this one says everything from above negative 2 all this way. So if you look at it carefully, you see if we still represent the negative 2 and the negative half, then you will see that intersection exists here. All right? For all values above negative half, we're going to have solution in both number lines. So that's where intersection exists. And so we say that what? I'll say that our solution set will be all real values of x such that x is greater than negative half. Again, this is the solution that we had with method 1. So whichever of the two methods we use, we will get the same solution set if only we keep strictly to the rules when solving inequalities. All right, so to answer our question, what are the set of values of x to which the geometric series will converge? Well, all values of x that are to the right of negative half, all values of x greater than negative half will make this geometric series to converge.